Hello and welcome to this abbreviated version of the presentation I'm going to be doing at VANZ this year, later this month in May, on controlling vibration with tuned mass dampers and tuned absorbers. So this presentation will be educational. It's just the very short version of it, in the hope that you'll actually come to the conference and hear the whole story. I'll be doing a few presentations there, and there's lots of other great presentations at the conference. So, as we're all aware, vibration can be a problem, either due to resonance or just because there's vibration coming from the machine. It might be unbalanced or just the engine vibration or whatever. And there are a number of solutions. One is to change the natural frequency of the system so we no longer excite the resonance, or we can add damping so there's not as much amplification, and we can try and control the unbalance or whatever the source of vibration is, and we can use isolation so that at least that vibration isn't transmitted through to the foundations. But there is another way, and that's with these tuned mass dampers and tuned absorbers, often called tuned vibration absorbers. So they're the same, but they're different, as we'll learn. And these devices are used in lots of applications. They're not necessarily the first place you'd go to solve a vibration problem, but hey, they're used in automotive applications. Like there might be a few of them in your car, in bridges, ships, buildings, power lines, and in rotating machinery and stuff like that. You'll see some examples later. So the basic principle is that we are going to add a single degree of freedom system tuned approximately to the resonant frequency, the natural frequency, or whatever that harmful frequency is. Single degree of freedom system just means it's going to be a spring and a mass and probably a damper. It vibrates so that the machine doesn't have to. And there is an example. This generator wall was vibrating axially, and this stopped it. Here's another case. This was a diesel engine. You'll see this case study a little later. And this thing vibrates up and down and stops all the vibration. So, tuned vibration absorbers are simply designed to absorb vibration, just motion. So it's a single degree of freedom system tuned to just the frequency of interest, the running speed of the machine, or whatever it happens to be. It's not a natural frequency it's trying to correct. Whereas a tuned mass damper is designed to focus on a natural frequency. Now in the case of tuned absorbers, we don't need to use damping, but in the case of tuned mass dampers, we can use damping or we don't have to. It just depends on the application. So here's a little video that sort of shows one in action.
Here we've got another single degree of freedom spring mass system with a forcing function. In this case we've got an imbalanced mass which is being spun. Although we're spinning it with fairly significant vibrations, it's not moving much because we've got a tuned spring mass dampener right here. So his resonant frequency is exactly the speed that we're spinning at right now. So Bob, the maintenance man here, can stand on the top of the building with the imbalanced air conditioning unit and not experience too much vibrations. If we spin it at a different speed, I'll adjust the speed now. Now you can see there's much more significant vibration at the top of this because we're no longer operating at the resonant frequency of the tuned mass dampener. And here you can see we're very far away from the tuned frequency, and we're getting significant vibrations of the building due to the imbalanced mass.
So there's more to that video. You can see that at the conference though. So here is a frequency response function, a single degree of freedom system. When we use a tuned mass damper, we tune out the natural frequency itself. Now this one actually has some damping as well. And when it's a tuned absorber, just the they call them dynamic absorbers, tuned vibration absorbers, whatever. We just create, again, a single degree of freedom system, but just to knock out a vibration, which would be right here. In this case, you see, this was the original system with the natural frequency. If all we do is add the spring and the mass to create a single degree of freedom sort of resonance, what we do is we completely split it. So we end up with sort of an in-phase mode and an out-of-phase mode, and there's a lot of attenuation right at that frequency. So if, for example, the machine running speed coincided with this this value, so it was amplifying, or the vibration was being amplified, and we used this solution, it would be a great solution. But any variation in speed, or if we operate here, we've got a natural frequency. If we operate around this frequency, we've got a natural frequency. Whereas if we use damping, we get a better solution. So to understand this a bit more, we're going to go into a little bit of theory, and in the class, or in the lesson I should say, or the presentation, we'll have more time. But hey, don't panic too much. It's pretty simple theory. The number one thing is we know if there's no damping, we can sort of add a spring mass system, and it'll just sort of bounce and bounce and bounce. We can adjust the stiffness to get the natural frequency that we want. We've bumped that up a bit higher, and we can add some damping to have the desired effect. That might have been too much damping. Yep, way too much damping. Anyway, let's just quickly do that again. Just a little bit of damping. Anyway, so that's the sort of a system we're going to add to the system. Now in this case, this little simulator just takes a moment to pop up. We can also then drive that system, and so in this instance, if I run it below the natural frequency, we don't get much vibration, but when we go right at the natural frequency, we get a lot of vibration. So look, it all depends on the amount of damping and so on. We see a certain phase relationship. We can look at the frequency response functions, but we'll do all of that stuff during the presentation. There's a lot to know. Now this is all looking very mathematical. I just wanted to put it in there so that you can have it in the slides afterwards if you want to sort of go back to any of this afterwards. But there are just a few things to understand if you want to actually understand how these things properly work, and if you were ever thinking about specifying it, or working with someone who would specify it. But there's some simple relationships. The natural frequency, either in hertz or just radians per second, is directly proportional to the stiffness, inversely proportional to mass. So anyway, there's we need to know what it means to be critically damped versus underdamped and whatnot, because we want to control the damping depending on the application. So here, this was the case where it was very lightly damped. You sort of saw that in the curve just before, and that would be the response of adding a single degree of freedom system to what is essentially an existing single degree of freedom system, and we end up with two modes. It's a 2 degree of freedom system now. But as we add more damping, we get a different response. So it doesn't attenuate as much right at the natural frequency, but it still does a pretty good job. Now again, this is getting scarier still, but the point is that when we look at the system, we can model it based on the stiffness, the damping, and the mass or the inertia. And with just a single degree of freedom system, we can say, well, there's one source of stiffness if we keep it simple, one source of damping, and one source of mass. With a multi-degree of freedom system, which is what we're going to be ending up with, and what really all the systems are that we're really working with, think of this as a matrix. We've got a number of modes, and each mode has certain stiffness, damping, and mass. And this is an important thing to understand. We'll spend much more time in the class looking at this, because if we're going to add one of these spring mass damper systems to a machine, we want to know what the modal mass is for that resonance. Now when we do a driving point measurement, we get a frequency response function, and depending on the units, in this case acceleration, but you'll see it on the next one. This is accelerance or inertance, and we can see, when we plot acceleration versus frequency, we get this shape. There's the natural frequency, and the shape of this is approximately, equal to minus 1 on mass. So we can actually determine the modal mass from this measurement. We can determine damping from it, easily from the velocity, and we can look at the stiffness from the displacement versus frequency, and we call this compliance, flexibility, or receptance. So in other words, we can just do a driving point measurement, put an accelerometer on, impacts it right at that spot, and we get all that information. It's great. You got to remember that the systems we're dealing with are multi-degree of freedom systems, but they are really just a combination of single degree of freedom systems. We can say, well, that's all we're really interested in, even though we know that these other modes exist. Now I'm rushing through this. As I mentioned, this is just the abbreviated version. This is what the frequency response function might be for a more complex system, but the situation we've got here is one of these modes is being excited and we want to do something about it. So even though there are other modes, we can treat this one just like a single degree of freedom system and then figure out all that stuff I just mentioned. And look, I'll explain this more in the class. The point is that we've got a complex system which we can break up into multiple modes, and we need to do that if we want to do this job properly. So when we do go through this process, the thing is that we can create a design that minimizes the displacement or minimizes the acceleration. And look, ultimately, if we were just doing this on a machine that was vibrating a lot, we don't have to get too sophisticated. We figure out the frequency, we tune it up, and then we fine-tune it to minimize the vibration of the machine. But we have to consider some other issues as well. There's the potential fatigue of the tune mass damper, and there's the issue, what would happen if our natural frequency varied at all, or if the machine speed varied at all. Do we suddenly get into those, is it going to amplify the vibration? What will happen? So again, without going into too much detail right now, this is our 2 degree of freedom system. Here is our machine, which for the mode of interest, remember we're trying to deal with one natural frequency, we've got its modal mass, stiffness and damping, and we put our tune mass damper on top, which has its own stiffness, damping and mass. That is a single degree of freedom system. And so ultimately we're going to have this vibrating, which was a problem initially because it's excited by a certain frequency. We're going to pop this on top, and the idea is to make it vibrate and this vibrate a lot less. That's our final 2 degree of freedom system. And look, I'm going to show you some equations and things. There's all the various parameters and annotation and so on. The thing is that we have to choose the mass of the tune mass damper to get the best results. And what I know, these equations will look a bit complicated, but they're actually not really. It's just, we use this little ratio here of the mass of the tune mass damper and the modal mass of the device we're trying to control, or the structure we're trying to deal with, and we sort of try to design it so the mass is about 5 to 10% of that modal mass. And these curves sort of show what happens when we alter the mass of the tune mass damper, and I will explain them much more in the presentation. And from that we can also then work out what should the frequency be of the tune mass damper. It's not actually the same as the natural frequency. We can also determine the optimal damping. Now again, this looks all very mathematical. It's just there for your reference. I will go through this in a sort of a more practical sense to explain the sort of the practical side to it, and the equations are just there if you ever wanted to use this information for a job. And from that we can also then work out the stiffness and damping of the system. Ultimately, with a lot of our applications, we're going to create something like this, and you'll see a picture of it later. In fact, you've already seen one. A bar with a mass, and that mass can actually slide along. And as you can see down here, the natural frequency of this system varies according to where I've got the mass. So you're going to do a design, get the stiffness of the bar about right, get the mass about right, and then just make small adjustments to tune it in exactly right. But we have to remember that the little tune mass damper is going to vibrate a lot, and so there are ways that you can perform calculations to make sure it's not going to fatigue as a result. And just for your reference, there are also some pretty fancy systems out there that actually control the damping and stiffness dynamically according to the operating conditions, and can therefore have the desired result. So some case studies. In this case was a reciprocating compressor. This is a real case, even though I made an animation of it. And it's vibrating, but it's vibrating both sort of, if you like, left to right and fore and aft. So it actually used 2 tune mass dampers to solve the problem, and the vibration went away, and these things just sat up on top and waggled. It was pretty hard to control it otherwise. Here we've got a generator, and the vibration was quite high, and then it was reduced by just adding this tune mass damper down here. Here we've got a control room sitting up on top of a structure, and the thing just swayed around and made the operators feel unwell. When the whole vibration signal was analyzed, there was this sway vibration of about 3.5 Hertz. And looking at the vibration as it varied, with process changes, the vibration sort of the structure changed, but it being amplified up in the control room, and the vibration was basically 3 times higher than the human comfort level. But a design was made. In this case, it was a fairly sophisticated approach taken, finite element analysis to find out, make up a design, look at what it was that they were trying to correct, and then design, in this case, basically a pendulum type system. Great big mass, and so you can see there's 3 of them along there. There's the control room sitting up on top, 3 of them. So basically, if you can imagine, as this swayed this direction, those swayed in the other direction, and it sort of counteracted that motion. It's just if it's designed properly, that's just the way it naturally works, and it was quite effective at reducing the vibration. So different damping, which was built in here. You'll see pictures of it. That's the actual sort of a test system that they set up with some damping in here, and that was the final solution, and it was quite a good solution, and that was the vibration afterwards. So within limits, it was all good. Here's another case study, and you can see the tune mass damper sitting on the side there. And this one is one from New Zealand. Simon Hurricks will be giving this as a separate presentation, telling that whole story. But another little example, this was the old Arsenal Football Club, and as the spectators jumped up and down, the stands vibrated a lot, so they added this. There's the damping, there's the stiffness, and there's the mass, and it actually stopped the football stadium from vibrating. They're actually used in transmission lines as well. You can see them there, and there's 3 ways that these the power lines themselves vibrate, but one of them is an up and down vibration, sort of a flutter if you like, and those things detuned that and stopped the vibration, because that's what actually causes cables to fail. In this case, we've got Taipei 101, great big tall building, but it experiences earthquakes. It's just near a fault line, and also these typhoon winds, and so they had to do something about it. So they made this huge 730 ton tune mass damper, and when you're in class, during the presentation, you probably couldn't hear me there, you'll actually see that thing vibrating when there was an earthquake. And this is without the tune mass damper. During an earthquake, and a crane actually fell off and unfortunately landed on some cars. Sad story, but it just shows the difference if you've got them or not. So tune mass dampers and tune vibration absorbers are a practical solution to high vibration. I've got some good references there. And thank you. Any questions? Any questions? No, I'm just kidding. Okay, so I hope you learned something from that presentation. I hope it was useful for you, but you'll learn a lot more if you come to the not-for-profit VANZ conference in Rotorua, and you can see the dates right there. Hope to see you there. I will obviously be there myself. Bye.